Also, thank you for sticking around to the end of the day to attend my talk. I really appreciate it. So today I'm going to be talking about iOS reverse engineering. My name is Patrick. I started my career at NASA working on software for the space shuttles and some of the Martian rovers. I then was hired by what I think is the only government agency that actually listens, the NSA. After that, I left with some of my friends to help found a small computer security company called VRL, or Vulnerability Research Labs. We were recently acquired by CSE. And currently I work for Synack, which is a startup that's actually located in California. I'm lucky enough to work remotely from Hawaii, which is amazing. So really lucky. Although red eyes to Boston, not that cool. But I really can't complain. So Synack is, what we do is we source a global contingent of vetted security experts that are all over the world, and we pay them on an incentivized basis to discover security vulnerabilities in our customers' web apps, mobile apps, or endpoints. So it's kind of like crowdsourced vulnerability discovery. We're always looking for new people, so if it's interesting, come talk to me. All right, so what are we going to be talking about today? It's really going to be a technical exploration of reversing iOS apps, focusing on finding vulnerabilities. We're going to start by talking about the iOS environment. Following that, we're going to talk about preparing a reverse engineering environment. Then, we're going to talk about some specific reverse engineering techniques, especially those that have to do with iOS reversing. And then finally, my favorite part is we're going to talk about some actual vulnerabilities that are in apps that are in the App Store today, and then also talk about some common bug classes and how to find them. I want to point out that this talk is really a compilation of public techniques. There's been a lot of research out there and some great talks recently about reverse engineering apps. So yeah, this is a compilation of that, but I hope that I've also enhanced it with some novel techniques, and also that because I'm showing some actual vulnerabilities and apps, it gives hands feel. Is this cutting in and out? You guys hear okay? Okay, cool. All right, so first the background, why should you care about all of this? Well, if you think about your iPhone or your iPad, it really has a ton of sensitive information. This is emails, photos, financial information, location. Really these devices are the gateways into the digital life. So they kind of have the keys to the kingdom. They have all sorts of credentials, passwords stored on them. This can be problematic if they get stolen. So there's been some recent studies that have come out, most recently by the FCC, saying that in larger cities, almost a third of all robberies are now attributed to theft of smartphones or cell phones. Another part of the study that was worrying is that almost 50% of these devices that get stolen are not secured with a passcode. What this means is even the most unsophisticated attacker can immediately access all information that's on this device. So if there's data that's not stored securely, this is obviously problematic. So I sleep with my iPhone under my pillow, so it's safe, right? Well, it turns out, even in your possession, the data on these devices might not be safe. And this is for a variety of reasons. First, network transmissions. If you're using a banking app that doesn't use SSL or uses SSL insecurely, this might be problematic. Or if you're using OpenSSL, apparently. Apps also process a lot of untrusted data, so if they're not written with security in mind or programmatically developed defensively, they might be vulnerable to exploitation. A lot of apps are also closed sourced, so you might be thinking you're downloading a certain app, but in reality it might be more insidious or suspicious and be gaining sensitive information without your knowledge. And then finally, if apps aren't securing data securely, and then you back up your app to your computer, that backup now might contain sensitive information. So if someone gains access to your laptop or is able to hack into your device, now they may get access to that sensitive information. So you can see there's a lot of threats, right? But this is 2014, apps are supposed to be secure now, right? Well, it turns out, you just have to look at the news and you'll find almost every month, week or so, there's a lot of vulnerabilities being reported. Banking apps are one. There was a recent study by IOActive showing 90% of apps that they looked at had some serious vulnerabilities. Social media, another one. A lot of credential theft, or the Tinder app allowed people to track users in real time. And then other apps in general. So there's really a ton of bugs. So these apps are really insecure. Well, what is the solution? I believe that reverse engineering can definitely help out for a variety of reasons. For one, it can help reveal vulnerabilities. I recently downloaded my mobile, my bank released a new mobile banking app that I reverse engineered, and I was able to find some vulnerabilities, so that kind of helps. You can also verify the app, determine, hey, is this really a Tor browser, or is it something that's just going to steal all my photos and my address book? It also raises security awareness. When you report a vulnerability to a vendor, hopefully they'll patch it, and hopefully they'll also take a more proactive posture and realize this is problematic, I should probably do some secure coding and maybe audit my apps. And finally, if you work for Synack as an external researcher and you find some bugs, you might get paid, which is always cool. So now I want to talk about the iOS environment. iOS is basically just OS X stripped down. Apple took their operating system, added a bunch of extra security, and then put some mobile magic, geolocation, touch events, stuff like that, and had iOS. From a reversing point of view, the extra security features are probably what's most interesting to us. And Apple introduced a bunch of these and actually did a pretty good job on them. So there's the secure boot chain, all code has to be signed. There's anti-exploitation mechanisms. When the phone is off, everything is encrypted. And finally, all apps and everything that runs is run in a sandboxed environment. So if we dive a little deeper into the security constructs around iOS apps, we see that there are several more that specifically pertain to apps. So again, all of this code has to be signed. All the apps have to be encrypted, although this is mostly for DRM-based purposes. And then the apps run as limited users, and they're very sandboxed as well. This sandbox means that the apps cannot dynamically generate any code or execute any secondary payloads. So they can't connect, for example, out to a web server and get some suspicious code that hasn't been audited by Apple. They also can't have, or they don't have any access to other apps' process space. So a malicious app can't inject into, say, Safari and steal its credentials. They also don't have access to hardware devices. They have to go through a well-defined API, which means, for example, if an app wants to access the user's location, it goes through this API, and Apple then can throw up a pop-up asking the user to confirm or deny. And finally, the apps are confined to the location or the directory they're installed to, so they can't access files outside this. So I want to talk a little bit about what actually is an iOS app. So iOS apps are they're distributed as IPA files. An IPA file is simply a zip file. If you change the extension to .zip, you can just unzip it with any unzip tool. Once you do this, you actually get the app. The app is really a bundle or directory that contains the app's files. And what are these app files? Well, it's obviously the app's binary, so the executable code, and then any other images or metadata that the app needs to execute. For reverse engineering purposes, it's important to understand an app's on-disk layout. So this is actually how it looks once it's installed. This is my banking app, Bank of Hawaii. You can see at the top there's the directory that it's installed to. If we then change into the directory where the actual app is at the top level, if we list the files, you can see there's the apps bundle. There's a documents folder, which is user data, which is backed up when the phone is synced to a computer. And then there's also this library folder, which contains caches, cookies, and other preferences, which is a good place to look for insecure data. If we then change into the actual app bundle, we can see again it's just a directory. There's the app's binary, there's a config file, and there's some other digital signatures as well. So apps are distributed as IPA files, and they contain a single app bundle. So you might wonder, how can they execute on, for example, older iPhones that run on 32-bit processors, and also newer ones, which are 64-bit processors? Well, the answer is the binary is FAT. So the FAT binary is the standard format for iOS and OS X. And what it does is it contains multiple architecture-specific Mach-O binary images. To figure out what's inside or the format of these, we can look at the fat.h file, which Apple makes available. These files start with this FAT-H, or this FAT header structure, which contains a magic number and then the number of architectures, which are the number of these architecture-specific binary images. Following the header are FAT structures. There's one for each binary within the actual FAT binary. And these contain a CPU type, a subtype, and then an offset within the FAT binary where the actual architecture-specific code is. So you can kind of think of a FAT binary as just an executable zip file that contains multiple architecture-specific binaries. These architecture-specific binaries are actually mock-O files. Mock-O is the standard file format for architecture-specific files for iOS and OS X. They start with a command, and then they have load commands, and then the actual executable code. So the header is a mock-O header, has a magic number, and then a bunch of other fields, the most notable probably being the number of commands. These commands, or load commands, are instructions to the dynamic loader that tell it how to lay out the binary and image, the initial thread context, and information such as that. And then following the mock-O header and the load commands is actually the raw data. So these are the binary opcodes and the data of the file. For reverse engineering purposes, anytime you're looking at a binary, it's really important to know or understand the high-level language. Apps are written in Objective-C. Objective-C is basically C with some object-orientedness added to it. So it's a superset of C, has different classes of methods. And that's how you say hi. Reverse engineering Objective-C can be challenging, and even the syntax of it looks a little odd. We're just going to briefly cover that. There's a lot of @ symbols and brackets. On the right, you can see the same kind of code, same chunk of code in C++ and then Objective-C. One thing to point out that in, say, object-oriented language like C++, methods are invoked. However, in Objective-C, we say messages are passed. So instead of calling a message on an object, you actually tell that message that you want to execute a method on it. So here's an example of a function declaration. On the left, you can see the return type. This is either going to be minus if it's an instance method, or a plus if it's a class method. There's then the return type, and then the method signature keywords, which make up the name or the selector of the method. The parameter types you can see pretty standard, although ID is the Objective-C, I guess, generic object type, kind of like void star in C. And then just the parameter names. So since it's an object-oriented language, it can be kind of a pain to reverse engineer. One thing that's really important to keep in mind, and you'll see this a lot when you're reverse engineering binaries, is that anytime you write some Objective-C code, or an application developer writes Objective-C code, when it is compiled, the compiler will actually take this code and convert it into this more C-like looking code that goes through the obj-C message send function. This obj-C message send function is documented by Apple, and it's important to understand the parameters because you're going to see a lot of these in disassemblies or when you're analyzing apps. The first parameter is the object that you want to invoke the method on. Following that is the name of the method, or the selector. And then if the selector takes any parameters, those come next. From a reversing point of view, this is a little bit problematic because all these Objective-C calls are going through this one method. So if you're an IDA looking at it, you're not going to see these API calls directly. You'll actually have to go back to where the obj-C message send function is being invoked, and then look backwards in the disassembly to figure out what object is being used and what is the name of the method or the selector that's being invoked. So let's talk a little bit about the ARM architecture. So all iOS devices run on processors based on the ARM architecture. ARM is a RISC-based CPU strategy, mostly fixed instructions. It's load store architecture, and finally it's encoded in various modes. These modes include ARM, Thumb, and Thumb2. ARM is a 4-byte instruction length. It's kind of the first or oldest encoding mode. Following this is Thumb, which is the 2-byte instruction length. Basically, ARM, the company, was trying to improve the code density on embedded devices, so they found a way to encode a subset of the ARM instructions. Most recently, there's a fairly new encoding mode called Thumb2, which has both 2 and 4-byte length instructions. And it achieves the same code density of Thumb, but the performance of ARM. So it's kind of the best of both worlds. ARM32 is the unofficial term, maybe my term, I don't know, of the ARM architecture on 32-bit CPUs. For reverse engineering, it's important to understand the registers and the calling conventions. You can see there's some general purpose registers, R0 through R12, and then there's other registers that are dedicated to specific instructions or actions. There's a stack pointer, a link register, and a program counter. The calling convention is pretty simple. R0 through R3 contains all the parameters, and R0 and R1 have the return values from a function. It's important to kind of remember these or jot these down somewhere because you'll see a lot of them when you're disassembling code. ARM64 is Apple's official term for the ARM architecture on 64 CPUs, for example, the iPhone 5S. It basically has just more registers, and instead of being prefixed with R, they start with X. There's also some dedicated ones for specific actions, so there's actually a stack pointer and a program counter. The calling convention, again, somewhat similar to 32-bit. X0 through X7 has the first 8 arguments, and then the return values, again, are going to be in X0, but can be all the way up to X7 if needed. There's this great article called ARM64 and You. It was written by Mike Ash. If you want to get more information on this, I would highly recommend reading it. So now I wanted to talk a little bit about preparing a reverse engineering environment, getting some tools and figuring out how to get and decrypt some apps. There's a ton of tools, luckily, for reverse engineering iOS apps, and I've kind of categorized them into 3 groups. The first one is for simple tools. These are basically common Unix or OS X tools that have been ported to iOS. The next group are these more advanced tools. They either have a little bit more of a learning curve, for example, IDA Pro, or they're specific to reverse engineering iOS or OS X binaries. And finally, and most recently, there are these comprehensive tool suites that are now starting to emerge. These tools do a good job of performing many of the same functions as maybe the more basic tools, but all in one spot. So this can be really good if you have a lot of apps that you want to triage quickly. You can just throw the app in these tool suites, and they'll spit out a lot of output. All right, well, what if you were to write your own, or if your favorite tool, for example, has a bug, doesn't run on iOS 7? Well, it turns out there's this great open development environment called iOS OpenDev. What it does, you can download it and install it, and what it does is actually patches or configures Xcode and sets up the OS X environment. You can then write some code, compile it, and then copy it over to your jailbroken device, and it'll just execute. So back in the day, you had to manually configure Xcode, which was a pain. You had to fake code sign all the binaries it produced. But iOS OpenDev does this all pretty much with a click of a button. So really beneficial. Definitely check it out. We'll now talk a little bit about programmatically getting apps for analysis and reversing. So obviously you can do this manually via iTunes, but this doesn't really scale well. So I thought, hey, I'm just going to sniff iTunes traffic, see what the parameters are, if there's an API, and then just put together a Python script to replicate this. So the first thing that goes out is an authentication request. In the request data, there's a name, a GUID, all pretty standard stuff. Following that, there's a buy request. Again, pretty much everything's standard except there's this one parameter, which I'm not sure if you can see it, but it's called KDSync, and it has some encrypted or obfuscated looking data. So I was I wanted to know what this KDSync parameter was, because that was pretty much the only thing that wasn't self-explanatory. So I Googled it, said, what is KDSync? And there weren't a lot of results, except for this one, which was pretty interesting. It was on a Russian forum, and basically it was a guy offering $10,000 for anybody to reverse engineer the algorithm. Now, in my reverse engineering experience, I found when a Russian offers $10,000 or something, probably not trivial to do. So I figured, I'm all about working smart, not hard. Well, I tell my boss both, but mostly working smart. So I figured there's got to be an easy way. So if we think about the basic workflow of iTunes when getting an app, what happens is iTunes will load the app in iTunes. It'll have the name of the app, screenshots, reviews, and then a nice big button that you can click for downloading or buying it. If you then click that button, iTunes takes care of all the authentication. It generates this KDSync parameter. And at the end, you have this the app. So I wanted to figure out how to programmatically do this. And it turns out it's actually pretty easy. So the first thing is we can use AppleScript and the iTunes Music Store protocol to load the app into iTunes. So in these 3 lines of AppleScript, we tell iTunes to open basically the app we're interested in. And you can get the link from the website, or if the customer gives you a list of their apps to test or reverse. Once you have it loaded in iTunes, all you have to do is enumerate the GUI widgets in that screen until you have found one that says download, and then you can trigger the download by clicking an element. So this is great because now you can automatically download as many apps as you want. So apps that are downloaded from the App Store, either manually or programmatically, are encrypted. And in order to perform static analysis, you want to be able to remove this encryption. The way that this is traditionally done exploits the fact that when you run the app on a device, or on a jailbroken device, the OS will automatically take care of all the decryption. So all you have to do is wait till the app is running in memory, attach to it, and then dump the bytes, and you have the unencrypted bytes. So you can do this manually via GDB, or there are some Cydia apps, or were some Cydia apps, that do this automatically. And the end result is that you have a decrypted app. Now this app isn't going to necessarily run because it's an in-memory image versus an on-disk image, but for static analysis purposes, it's pretty much all you need. So I wanted a method, though, that gave me a little more fine-grained control. Basically, I wanted to be able to do this programmatically. So again, remember, what we want to do is we want to execute code within the app's address space on a jailbroken device. We then want to dump the now decrypted app's code to disk, and then the end result is the decrypted device. So again, I Google this. I guess I do a lot of Googling at my job. And I found this dumpdecrypted.c file by Ionic that basically achieved exactly this in 2 steps. It first used an environment variable that you could set that points to your dynamic library that would be automatically loaded within the app's address space whenever the app started. If this dynamic library exports a constructor, this will be automatically called when it's loaded. So in this constructor, what you can do is you can just scan the address space, find the app, and then if you parse the mock-o header, you can find the offset within the file where the decrypted, well, now unencrypted code is, and you can just dump that to disk. So this is a great way to programmatically decrypt the app. And now once it's decrypted, we can actually talk about some reverse engineering. So I want to talk about some reverse engineering techniques, specifically some that apply to reverse engineering iOS apps. When reversing an iOS app, the first thing I usually do is triage it, kind of get a general sense of what it's doing. And the O tool is great for this. So if you run the O tool with the -F or -H flag, it'll give you the mock O and fat headers. If you run it with the lowercase l flag, it'll give you all the load commands. If you run it with the capital L command, it'll give you the dependencies, so the libraries that the app loads. This is useful because it can tell you, for example, if the app is going to make database queries, if it's going to access the address book, so on and so forth. And finally, if you run it with the lowercase o command, it'll give you the class names and method names that the app is using. ClassDump you can kind of think as a specialized O tool. It provides an easy way to find interesting variables or methods. Basically what it does is it can display the Objective-C interfaces and declarations. So again, we can see I ran it on my banking app, and it is able to spit out all the interfaces, the names of the instance variables, and then the names of the methods. So what you can do is you can look at this output and then find either method names or instance variables that appear interesting, and then go look at those in disassembly to see if they, for example, implemented password storage correctly. So IDA is the de facto reversing tool. I'm sure you're pretty familiar with it. And it does a pretty good job now of reverse engineering Objective-C. In the last few years, it's definitely made a lot of progress. So if we start with some Objective-C code, this is just the line of code that we want to basically put the current date into a string. If you compile this, it's going to break down into these 2 separate lines of code that both invoke the obj.c message send function. So first it's going to do that to generate the date object, and then following that, it's going to do that, take the date object and put it in the format string. So if you take a compiled app, throw in IDA, it'll produce some pretty readable disassembly, although it might be kind of small. You can see at the very top what it does is it loads the address of the obj.c message send function into the R9 register. Following that, it's going to set up the parameters. So the second parameter is in R1. This is the name of the selector that we're going to call, or the date method. And then in R0, this is the first parameter. This is the object we're going to invoke. In this case, it's the NSDate class. Then all the way near the bottom, you can see the BLX R9. And what this is doing, it's invoking the Objective-C message send function with the specified parameters. And then once that function call is done, it stores the result in a stack variable. And this return value is going to be in R0. For the next line of code, this again is putting that result into the NS string. Again, very similar. They load up the address Objective-C message send into R9, and then set up the various parameters in R0, R1, R2, and R3. And again, once they call BLX R9, R0 is going to have a formatted string. So this is definitely a good way to figure out what exactly is going on, this static analysis, but it can be tedious and slow. But it will give you a deep understanding, and you will uncover some serious bugs if they're there. But there's got to be a quicker, faster way. And it turns out dynamic analysis is definitely this. We're going to talk about several types of dynamic analysis. The first one is network traffic analysis. The second one is going to be file system I/O. The third one is going to be debugging, and then finally we're going to talk about instrumentation, instrumenting the actual app. So network analysis is a dynamic analysis technique that is a good way to collect network traffic. It requires the setup of something like a proxy to intercept traffic. It's pretty conceptually simple. The way you actually do this for an iOS device, well, it turns out there's two main steps or components. The first is configuring the actual proxy. This is really straightforward. Just take your favorite proxy, set it up. I use Burp. It's a free proxy. Pretty much click it, enable the proxy, and it's good to go. The one thing important to note is the port, which is 8080. Once you have the proxy set up, you can configure the device. And there's two main steps for this. The first is to install the proxy's SSL certificate, or self-signed certificate, on the actual device. This is needed because iOS doesn't trust self-signed certificates by default, so what you have to do is install the proxy certificate into the proxy chain on the device so that SSL traffic or SSL connections won't be broken. Once this is done, you can actually configure the device by setting the HTTP proxy and just put in the IP address of the server and then the port. At this point, most SSL connections will automatically go through the proxy, and you can examine all the traffic to make sure there's no insecure data or that everything that is sensitive is actually secured with SSL. Monitoring the file system is actually another really powerful dynamic analysis technique. It can show you what is written or read from the file system and also what files the app is using. This is really powerful because you can see which files it's accessing or creating and then manually go look at those files to see, hey, are there usernames and passwords in there or other information that's sensitive and not stored securely. So how do you do this practically? Well, there's a great tool called FileMon, pretty similar to the Windows FileMon. You run it on a jailbroken device, and then if you run an app or any program, you can see the output, and FileMon will just grab that and dump that to standard out. So here I ran the Bank of Hawaii app again, and it created some files, moved some files around, and renamed them. So pretty straightforward. There's one problem. On iOS 7, it crashed, it segfaulted. Turned out the author who released this as open source, again, he did a great job, but he forgot to handle a certain event type. So if you add those few lines of code, it will run on iOS 7 as the author intended. And again, I used the open iOS dev to do that, and it was really straightforward. So debugging an app, again, another dynamic analysis technique that can allow you to watch as code executes instruction by instruction. Pretty easy. You attach a debugger, you execute the app, and you see the instructions, set breakpoints, poke around in memory. GDB is the standard de facto debugger that's used on OS X, Linux, and also iOS. Since there are some iOS-specific techniques or things that come into play when reversing apps, these are just some kind of hints or tips that I used that were really beneficial to me. So I found the easiest way to debug an app is actually just wait until it executes and then attaches it. If you try to run it directly under the debugger, sometimes it has issues and path issues. So this is just the easy way. So if you run GDB with the wait for flag and then the app name, it'll automatically attach when the app is ready. Once you're attached, you can give it the info share command, and this will display all the loaded modules. This is important if they've been relocated for ASLR purposes. You can get the delta offsets, and then you can rebase the program in IDA Pro if you're trying to follow along doing static analysis to get the addresses to match up. Since Apple's GDB doesn't support the forced thumb mode, it has problems disassembling thumb code, so you have to explicitly tell it when to decode instructions as such. And you can do this with the -H flag. And finally, the most powerful, in my opinion, command, maybe besides editing memory or breakpoints, is the PO command. And this basically tells GDB to parse or treat a specific address as an Objective-C object. And then it's actually able to print out a lot more information. For example, if it's a dictionary object, it can print all the members in the dictionary. So again, this is a pretty powerful thing to do. One thing to point out, the version of GDB that's in the default Cydia repository doesn't play nice on iOS 7, so there's this other one that someone else has compiled that works a lot better. Another really powerful dynamic analysis technique is app instrumentation. Instrumenting an app basically means injecting code or an interpreter directly into a running instance of an app. This is really powerful because what it allows you to do is bypass client-side logic, execute hidden code, or even manipulate the app runtime. Script is the de facto tool for this. You can download it pretty easily, and then once it's installed, you can execute it with the P command and give it the PID of the app that you want to inject into. Once it's injected into the app, it gives you this interactive console which you can execute commands at will. It's almost like in Chrome or Firefox, if you're using the development tools, you can examine the DOM tree and you can manipulate elements within that. Conceptually, the same thing. Just want to show a really kind of simple example of this to illustrate what you can do. This is a screenshot of my banking app. Since I'm a poor reverse engineer at a startup, I only make $100 a year. But I wanted to impress people, show them that I make a lot of money. So what I can do is I can find the text field in the app that contains that, and then using script, I can just manipulate it at will and change the values. When you're reverse engineering, testing, fuzzing, this is a very, very powerful technique. All right, so now my favorite part of the slides, I want to talk about finding some common vulnerability classes, or classes that you're going to see a lot, and then actually show you some apps that are vulnerable to them. First, I just want to reiterate the mindset. Targeting mobile apps, it's not about installing implants that mine bitcoins, building a botnet. It's really gaining access to that sensitive information. And there are a lot of threats. Theft is obviously one. There could be network monitoring that's going on, backups if they're insecure, and finally, if there's malicious apps, they might be accessing this information. So network security obviously is a big one, and first how to do it correctly. SSL, anytime sensitive information is being used, use SSL. Hopefully Apple doesn't have another go-to fail, or OpenSSL fixes their problems. But assuming that's good, just use SSL and use it correctly. Also, it's really important to sanitize anything that's coming off the network. Apps a lot of times will render content directly in a browser window internal to the app. And so if an attacker can inject JavaScript or HTML, this can lead to traditional browser vulnerabilities like cross-site scripting. So the first thing to do is look for if the app implements SSL and if it does so in a secure manner. Luckily, iOS enables SSL for any HTTPS link. So what this means is if the developers, or if you see a lot of HTTPS links, it means it's using SSL. Now, if you see some that are not, if they're just HTTP, it might mean that part of the communications are not secured. Even if you do see SSL links, though, the developer might allow self-signed certificates. Now, this isn't on by default, but there are methods that can be called that a developer can actually invoke in their code that will allow them, the app, to handle self-signed certificates, which, as we all know, is a bad idea. So here's an example of a broken SSL implementation. This was an app that we audited, and so unfortunately I can't provide the name. But it invoked the set allows any HTTP certificate for host method. So what this meant is that this app was vulnerable to a self-signed certificate. Another problem, or another way you can actually find SSL vulnerabilities is just to sniff the network traffic to see if it's using it incorrectly. So I was looking at my Bank of Hawaii app, and I noticed that one of the connections that was going out was actually an HTTP link. All the rest were HTTPS. And this was also logged in syslog. They did a nice job providing me with this debugging information. Turned out this content, or this request, was going out to get HTTP content that was then displayed in the app. So what I was able to do was provide an alert message and then an input screen that looked like the one that the user was provided when they logged in. So this is an actual screenshot of the attack. Again, this content was being rendered directly in the app, so I was able to inject this code. The other thing is, if you think of a browser, if there's this code injection going on or it's taking you to another site, there might be some indicators of that. However, in an app, users are a lot more likely to just trust what the app says. So if there's a pop-up in your banking app saying something's expired, you're probably not going to think twice about it. So besides SSL, there's also other network security issues that are worth looking for. Cross-site scripting is a fairly common one. An older version of Skype had a problem where an attacker could basically inject code into the name of the user you were talking to. And then server-side APIs. If you're reverse engineering an app, you can look to see what it's connecting to and what APIs. Snapchat was a great example. They weren't throttling an API or authenticating it, so phone numbers could be stolen. Next thing I want to talk about is insecure data storage. First, how to do it correctly. Well, on older versions of iOS, the data partition was fully encrypted. So this meant anytime the phone was off, everything was secure. Problem is, whenever the device is turned on, the operating system automatically decrypts all this information without requiring a username or password. Apple realized in iOS 4, I believe, that this wasn't a good idea, so they added a second layer of encryption. Basically, that was based off the user's password. And this meant that when the device was locked, all the protected files were inaccessible. So this is how to do it right. Problem is, a lot of people don't use this technique or store their data in other locations. So apps will store sensitive data in the binary itself, withinplists, within databases, or even within log files. So within the binary, a lot of times if you're reverse engineering a binary, you'll see usernames, passwords, hidden in there. PuffChat is a chat client, kind of like Snapchat is the pictures. You can text people stuff and it goes away. Turns out, though, they hard-coded an authentication key in their binary. There's kind of a funny quote from the guy who found this bug saying, don't store things in a binary. It's even funnier when it's not obfuscated. So again, it's always good to look in the binary to see what you can find. P-lists are another common place that things are stored. P-lists are just XML lists that are used extensively. The most common one is this user defaults list. So iOS or Apple provides an easy way for app developers to store persistent data. So this is supposed to be used for things like what color did the user select, do they want 24-hour time, stuff like that. And you can see in one line of code you can store data to the P-list, and another line you can retrieve it. The problem is this P-list is not secured with a second layer of encryption. So if the user loses their phone, an attacker can just jailbreak the device and all this information will be unencrypted when booted. So to spot the disassembly, or to spot a vulnerability like this, you can look for calls in disassembly that reference this user default plist, or you can just run filemon to see if they're writing. This is an example of, kind of hard to see, of a healthcare provider app that we were auditing, and it basically was storing a session key into this unencrypted plist. I was able to take this session key and plist file, put it on a brand new device, and automatically log into the user session without a username and password. So again, definitely something to look for. Databases are another great example. If the application developer has not opted into the second layer of encryption, any database or information they're storing in a database could be potentially retrievable if the phone is ever lost or if it's compromised. It's pretty easy to see if the app is using the database. Just run filemon, see what files it's writing to, or you can look if it's importing the SQLite API. This is WhatsApp chat. Again, kind of hard to see, but basically they store a lot of the chat histories in a chat storage.SQLite file. This is all unencrypted and available. So again, if you lose your phone, this information is trivially recoverable for an attacker. And the last one is within a log file. A lot of times developers will actually store sensitive information into a log file, I guess for debugging purposes. To find if the app is doing this, you can again look for file IO APIs or just run filemon. And here's an example of this. On the left is a disassembly showing the file APIs being used. And then if you go and look at the log file, again, a little hard to see. But again, this was another app that was logging a CSRF token and a session ID to this log file. They were basically saying, printf, these are these values. So again, an attacker could access this. The phone was lost or stolen. It wasn't secured in any manner. So again, not secure. It's also good to sometimes just tail syslog. A lot of apps will just spew data there. You get lucky, find some information. So network security and data at rest security are probably the two biggest vulnerability classes, but there's tons of others that aren't as common but are good things to look for. There can be cookies that contain sensitive information if the app doesn't clear those out. Similarly, if requests are cached, there can be usernames or passwords or authentication cookies in there. Apps might also make use of IPC, and if these endpoints aren't secure, or you can audit them and maybe find some information. And then lastly, every time you press the home screen, the iOS will take a screenshot to help, I guess, make the animation look pretty to going back to the home screen. So if you have a sensitive app and you're chatting, or your banking app, and you have sensitive information, and the app should opt out of this method to protect that sensitive information. Alright, so hopefully I've shown you that insecure apps are everywhere. Currently, iOS security, at least for third-party apps, is really an afterthought. And using the techniques I've described in this presentation, you should be able to start auditing your favorite apps and find lots of bugs. So I have 1 minute or so, but this is the last talk of the day. So are there any questions? Also, I'll make these slides available if you want to go back and look at some of the specifics. I know some of the stuff is kind of hard to see.
Where are the app files going to be available?
I think on the source website. If not, I'll give you my business card. You can shoot me an email, and I'll send them off. Yeah?
So what's your approach for attacking applications that don't use the certificate key store on the device? So recently I was on an assessment where I had an application that, for the majority of the requests, the SSL, was pulling certificates from the root certificate store on the device.
Sure.
But then there was a library that was compiled in that had its own certificate baked in with it, and all calls to that server, were basically being validated. So I was having a pretty difficult time actually intercepting that traffic because all my techniques to get my certificate on there and do redirection and stuff just wasn't working. Kind of, what's your approach for tackling potentially libraries or stuff that ship with their own key stores and aren't going to listen to the device's key store?
Yeah, that's a great question, because another thing I didn't go into a lot, and I haven't seen this a lot, but also if apps do SSL pinning, the proxy technique isn't going to work. So something like that would be challenging. Luckily, I haven't run into that. Knock on wood. I think maybe some of the debugging techniques, or maybe the app runtime instrumentation, you might be stuck, knopping out checks or something. I mean, if it's OpenSSL and it's passing certain flags to set it up, I looked at one app that was doing that, and I just patched or changed the flag to basically say allow third-party certificates.
Right, and I actually had a...
Yeah, how did you solve it?
I had access
The source, so I just turned I turned SSL validation off. It was a C++ library, and so I went in and basically just turned off the methods that did the certificate validation, so it would basically allow any sort of certificate if it was signed, unsigned, etc.
So you probably...
I was just kind of curious that in the event that you didn't have source code, like what kind of approach would you use to tackle that?
In the past, I've had to actually go in and patch those bytes, kind of what you did in source on the binary. There's also another tool, I think it's called SSL kill switch, but I think that's more for bypassing when they're doing pinning, but I don't know if that would apply to the same situation. In the back to the left.
So one of the common techniques to harden mobile apps is obfuscation.
Sure.
So I'm wondering what you think of that, and how often you see obfuscated apps in the field, and if you do, which software tools are being used to obfuscate them?
That's a great question. As a security professional, I would say obfuscation in general is just kind of security through obscurity, which isn't too much of security at all. I have seen some cases where keys or certain strings that were related to authentication were obfuscated, so that if you just dumped strings on the binary, you couldn't see it. I haven't seen it that much. I see a lot more in OS X malware or Windows malware or anything like that. In apps, I think a lot of people who are writing the apps are kind of new to it, within a year or two, so obfuscation hasn't really advanced to that stage yet. To techniques to basically get around it, anytime I see strong obfuscation, I look for runtime techniques, so the app instrumentation or debugging. I'll just basically, if there's a string or a key that's obfuscated, I'll just basically run the app and set a breakpoint to right before it's being used, and in that point it'll be deobfuscated. So kind of like how we decrypt the apps, we just let the OS load them and decrypt them and then dump the memory. That's, again, the same technique. I'm not sure of, or I don't know of any iOS or Objective-C obfuscators that are out there. You'd think there would be more, because Objective-C puts in a whole bunch of runtime type information, kind of like C++, class names, method names. In OS X, I've seen code that obfuscated those, but I didn't know if there was a tool that was available to do that, or if it was just a precompile step or something else that they were doing. But again, you see the obfuscations mostly at runtime. You can just let them get around them. That's more over here.
So in looking for exploits and bugs and things in reverse engineering, have you run into anything that wasn't necessarily something shady? Like maybe this app shouldn't be doing this. Why are they doing this? What's going on here? And could you talk about that?
Yeah, definitely. So I think that's probably more common than we, the general public, are aware of. So Apple will verify an app, and what they do is they just make sure you're not using private APIs, that there's no adult content in there. But other than that, they're not looking for security bugs or even suspicious behavior. I haven't seen that personally yet. A lot of times, Synack, we're auditing apps that the customers are giving, so they own the app, so unlikely. But what's up or WhatsApp app was rumored to be accessing the user's address book without telling them and exfilling that or grabbing that, and people are saying maybe that's why Facebook bought them. But I write some mobile apps, and one of my apps needs to access the photo editor or the pictures in the screen. Or in the photo thing, and there's nothing to keep me from just stealing everyone's photos. I'm a moral person, so I don't do that. You have to trust me unless you reverse engineer the app. But I haven't seen a lot of that, but I think there probably is a lot of that out there. It's kind of abuse of that. I mean, there's a lot of sensitive information that just from advertising point of view that I'm sure companies would like to get. So I think there's probably a lot of that, but hopefully reverse engineering could reveal that. I'll let you know if I find some, though. Sure. Yeah.
I just went on an Android assessment a couple months ago, and it was basically an app that connects to a document repository.
Okay.
And so the user could download the document, view it locally, and do whatever they needed to do. But I noticed that when the user logged out, those files were persistent. And my first gut reaction was, oh my God, bad developer, encrypt that data. And then I started thinking about it, at what point does the responsibility of that end for the developer, and then the vendor of the device pick it up, or the user pick it up? And I wanted to get your thoughts on where those demarcation lines lie.
Yeah, and that's a great question, because the user default plist, I would say, is a great example. Apple says don't put secure information in there, so I think that one you kind of blame the developer. But when you press the home screen, it takes a screenshot. Unless you go read the Apple specs really closely, you're not going to know about that. So if there's secure information and then the user presses the home screen, that's almost like an iOS issue. Apple kind of goes back and forth on this, saying, oh, the developers are supposed to know this. The developers haven't written as many or as much code for the environment. Sorry, so they're not aware of that. I think Apple has done a pretty good job. They definitely could go a little further. Where that line is, that's a good question. I would like to see Apple just encrypt everything. Require a passcode. But again, it's just a trade-off between users and whatnot. So I think it's kind of split right down in the middle, where Apple does a pretty good job but could do better, and I think the developers also screw up a lot because it's kind of a new platform for developing. So it's kind of good to know where those lines are, and then see who makes assumptions about the other person doing, and then that's a good source of bugs, kind of like you were saying with the app you looked at. Any other questions? Well, thanks again for listening. My email address is patrick@Synack. Check out Synack.com. We're always looking for new researchers, hiring, get paid to find. A lot of bugs. These apps are just horrible, so we have people making some good amounts of cash. So, well, thank you again.
Please make